Hi guys, and welcome to topic 8.1. So this unit is going to focus on chemical reactions, and for the next kind of first few days of this unit, we are going to start working on how to balance chemical reactions. Today we're going to start kind of with simple reactions, get the process down, and then as time goes on, we're going to move into more difficult reactions on how to balance. And so we talked way back at the beginning of the year on the difference between a physical and chemical change. And so we're really going to emphasize chemical changes now for the remainder of the semester. And so we can describe a chemical reaction in which one or more substances, and what I mean by substance here is that it can be pure substance as an element or compound. So we can change elements or compounds into new substances, as in an element can react with something else to form a compound. Maybe a compound breaks down and it makes elements. We can have different compounds rearranged. And so we're going to study all of those different scenarios in this unit. So an important term that we use in this unit is a reactant. And so this is material that starts the reaction. And so, for example, when you take in oxygen, your body is using a sugar and combining it with that oxygen to produce carbon dioxide and water. So the sugar and that water that you talked about back in or sugar and oxygen that you talked about in biology and cellular respiration, or you talked about photosynthesis as well. Those starting materials are reactants. When a reaction is complete, that is where you get new products. And so that is what is formed because of the change. And so that's one thing we'll identify today is what's a reactant versus a product when looking at a chemical equation. Just a very, very general layout when we look at a chemical reaction is it has two parts. The reactants, those are what's found left of this arrow, and then we have the products that are normally found on the right. This arrow can be interpreted as a couple of things. We can say that that means forms, we could say produces, but oftentimes in chemistry we say yields. So reactants yield products, or reactants form products, or reactants produce products. So again, this is kind of like an equal sign almost in math, that we're going from one to the next. So from there, the whole reason why we have to show balanced chemical reactions is to conserve mass. So we discovered the law of conservation of mass in that we cannot chemically create or destroy matter. Now, nuclear chemistry gets into how we can change mass into energy. We've been there, done that, talked a little bit about it. We're leaving that in the past. We're talking about chemical change. So chemically, we cannot create or destroy mass. And so the amount of mass you begin with on the reactant side is equal to the mass on the product side. Most of you probably did in elementary school, like the volcano, where you put the baking soda and vinegar together. So vinegar is acetic acid, baking soda is sodium bicarbonate. When you react the two, you get the big foam, which is showing the carbon dioxide that's being released is one of the products. Water is another product. And so the idea is if we were able to put that all in a Ziploc baggie, get the mass before we've mixed the two, combine the two together, get the mass after it, and we've collected everything, that mass is going to be the same. So in a chemical equation, some more terminology that we're going to see today. Formulas and symbols we're familiar with, but we're going to add coefficients today. You've probably seen the term coefficients maybe in math. We're going to use it probably in a different frame than what you see again in math. And so it's going to represent a unit. And that's going to become very important as we snowball again forward. Chemical reactions are going to carry over with our next unit, moles, into the wonderful collaboration that is stoichiometry, where we look at moles or quantities of matter. So we're going to get back into the math here pretty soon. And so mass is always going to be conserved, and so coefficients are added to balance the equation. So if you start with 5 atoms of hydrogen, you must have 5 atoms of hydrogen on the product side. Just a few terms to remember. When we go back to our chemical naming days, our H and our O, we know that stands for hydrogen and oxygen. So again, when we look at a chemical formula, we have symbols there that identify the elements that make up the compound, if it is a compound. We also know because of charges or because of the different naming rules that we do have subscripts, and that tells us a quantity of how many we have. So we know that this is made up of 2 hydrogen and 1 oxygen. And then this is that new term for today. This is a coefficient, and that's how many molecules you have. So we have 2 entire molecules of water, which are made out of 2 hydrogen and 1 oxygen. And that's what we're going to practice with here in this next part. So before we can start balancing, there's some things that we need to discuss in order for balancing to make more sense. So we need to interpret subscripts and coefficients here, and how does that apply? And so from here, what we have is this formula for carbon dioxide. So it wants us to circle any subscripts. We're going to box in any coefficients and then answer the adjoining questions. So here we can see right away that we have a subscript on the O, and that's that 2. So I'm going to circle that. If we had a coefficient, there would be one to the left of the formula, which we don't see, so there's nothing to box in. So then it's asking how many atoms of each element are in the formula. So here we have our CO2. There's no subscript, so we have 1 carbon. When we look here, we have a subscript on the oxygen, therefore we have 2. Moving on, we have our next one set up with 5H2. So again, as we take a look at our formula, I see a subscript here of 2. This case, we finally do see a coefficient, this 5 to the left. And then we're going to answer it. It asks, how many hydrogen atoms are there? So this works a lot like math. We're going to use distribution. So we multiply the coefficient times our subscript. So 5 times 2 tells us there are 10 atoms of hydrogen. So same idea here. We do have 2 subscripts. We have a 2 on the carbon, and we have a 6 on the hydrogen. We do have a coefficient here. That coefficient is 2, and again, it distributes to each of these. So what you need to be careful on is the coefficient, again, applies to all elements in the formula. And so when we take a look at the carbon, we're taking a coefficient of 2 times a subscript of 2. Therefore, there are 4 carbons. In hydrogen's case, we still have that coefficient of 2 applying to it, and we have a subscript of 6. So 2 times 6 tells me that there are 12 hydrogens in this formula. So here I realized I goofed up, that this is not correct because of charges, but we're going to just roll with it. If you really wanted to get nitpicky, the formula should be AlPO4, but I was trying to go with a process where we have parentheses. So we're going to just pretend that these are the right charges, even though, yes, I realized I goofed on my end. Okay, so we have 3 elements. We have aluminum, we have phosphorus, and oxygen. So we need to know the quantity of each of them. We do have some subscripts. We have this 2, we have this 4, and we have this 3 outside. We do have a coefficient to the front. So the coefficient distributes to each individual element, but we also have more distribution going on than just that. This 3 that's outside of the parentheses distributes to what's inside of the parentheses. So to be careful, when we start with aluminum, for example, this part's easy because the parentheses do not apply. Coefficient 3 times the subscript 2, we have 6 aluminum. When we move over to the next one, and I was trying to color coordinate this, and I'm fighting my own system. Okay, so we have 6. Now, when we move on to the phosphorus, this 3 distributes in from the parentheses, so a subscript of 1, so that's 3. Then multiply by the coefficient. 3 times 3 gives us 9 phosphorus atoms. Now here, we have a subscript 3 here. So we distribute that in and multiply it times the subscript that is already associated with oxygen. So 3 times 4 is 12. I then apply the coefficient to it. 12 times 3 gives me that there are 36 total oxygen atoms within 3 molecules of this aluminum phosphate, if that was the true correct formula. Okay, so that part's going to apply to the big idea for today. And so, like I said, the general equation for a reaction shows that reactants are on the left of this arrow. And like I said, one way that you can translate or interpret an arrow is yields. And anything to the right of the arrow is a product. So here, we can identify the reactants as R or products as P. So the first thing is you find your yield sign. Anything that's to the left of it is going to be a reactant. So I can see here that my H2 and my O2 are to the left of the arrow, therefore they are reactants. Anything that's on the right of the arrow, again, kind of like an equal sign, is a product. So in this case, we only have one product, which is water. Here in this equation below, here's my arrow. I only have one reactant. The ammonium nitrate is the only symbol, or in this case, formula, to the left. I do have multiple things to the right. My nitrogen, oxygen, and water are all to the right. Therefore, those are all products of this ammonium nitrate breaking down. The last thing before we start balancing is just a quick review on the vocabulary. So I'm going to start here with this box, and it's pointing to the Mg and to the oxygen. So what that's indicating is these are the two starting materials. Therefore, this is the reactants. This is what is starting out. From there, as we make our way around, this is again like our arrow sign dividing our reactants from products. This is yields. And in this case, it's pointing to the MgO. That is what is formed because of the reaction. So this is the product. Here, it's pointing to the 2 that's in the front, leading in front of your chemical formula or symbol. So that's a coefficient. And lastly, we have this 2 associated with a symbol. It's written below, so we know that's a subscript. All right, so now we're ready to balance now that we have our vocabulary. So what you're doing here is we are going to be adding coefficients to this reaction in order to show that mass is conserved. So the first thing I do is I draw a line to separate my reactants from my products wherever my arrow is found. The next thing you need to do is we need to take an inventory, listing out the elements that we have. Again, we're starting with baby steps today. I would like you to do this process because where we're heading. Again, I can see the big picture, and you definitely need to start with this process. The next thing is order. Kind of like with Lewis structures, there's a right order to things. And so the one thing you do want to make sure is oxygen can send you on a wild goose chase. So always start by balancing anything that's not oxygen. So we have 2 things in our reaction, sulfur and oxygen. When I look at the reactant side, I can see that because there's no subscript here, I have 1 sulfur. However, I have a subscript on my oxygen, I have 2. I'm going to take an inventory with the product side, doing the same thing, listing them in the same order as the reactant side. So on the product side, I have 1 sulfur and I have 3 oxygen. So our goal now is to add coefficients to my reaction in order to make it equal. I can see here that I have 1 sulfur atom on each side, therefore it is balanced. Here I have 2 and 3, they are not balanced. However, I can add coefficients to take care of this. You can never change the subscripts on anything, whether it's an element or a compound. Your subscripts are locked into place. You can only add coefficients. So here, what you can do is you need to add a coefficient to make these equal. Now, my chemistry teacher in high school, she liked to balance with fractions. If you're like me, I'm not a huge fan of fractions. If you figure out the fraction method, I am completely fine with that. My brain just works better with whole numbers. So what I look at then is what do these both go into? So 2 and 3, I know both go into 6. So what coefficient do I need to add here that will multiply times 2 to get to 6? That's going to be a 3. So what I do is I don't erase this. I just put a slash through it and update my inventory. That has changed to 6. I need to do the same thing to make these equal on both the reactants and product side. So I'm going to multiply this by 2 because I know 2 times the subscript of 3 is 6. However, when you add a coefficient, it applies to anything in the formula. So we also now have 2 sulfur. So sometimes you have to go back and rebalance something that may have been balanced right away. What I know, what can I multiply times 1 to get to 2? That's going to be a 2. What I'm then looking for is everything equal. So I have 2 sulfur on each side. I have 6 oxygen on each side. And I now have a balanced chemical equation. So with our next example, we have kind of the same idea going. My first step is I divide my reactants from my products. I'm going to take an inventory. Oxygen is present, so I'm going to list that second. I'm listing them in the same order, reactants, product side. I have 2 and 2, 2 and 1. I can see my nitrogens are equal, therefore they are balanced. My oxygens, however, are not. I have 2 on the reactant side. I have 1 on the product side. That means I need to increase my number on the product side to balance it out. So I'm going to add a coefficient here of 2. When I do that, that gives me 2 oxygen. But again, I've now impacted or changed my number of nitrogen. I now have 4 nitrogen. Therefore, I need to balance those on the reactant side by adding a coefficient of 2. I now have a balanced equation because my nitrogens are equal and my oxygens are equal. Now, you have a couple things you can do with this. In algebra, typically you write x. You don't usually write 1x. That 1 is implied, okay? So what we're showing here is that that 1 is implied. So oftentimes you will see this is saying 2, 1, 2. The 1 is there, but if you would prefer, you can write a 1 in, but it is not necessary. Okay, example 3. Same pattern. Divide your reactants from products. Here we don't have oxygen, so order doesn't matter. So I'm just going to list them in the order I find them, sodium and iodine. I have 1 sodium on the reactant side, 2 iodines on the reactant side. 1 sodium on the product side, 1 iodine on the product side. My sodiums are balanced. My iodine are not. Product side is only having 1, so I'm going to add a coefficient of 2 here. Again, my coefficient impacts everything, so I also now have 2 sodium. That means I need to put a coefficient of 2 here, and this balance is very similar to the equation in example 2. Again, you have 2 options here. You can leave it blank or write in a 1, whichever is your preference. Next example, we have aluminum combining with oxygen to make aluminum oxide. We have aluminum on the reactant side with 1, oxygen with 2. On the product side, aluminum we have 2, oxygen we have 3. I can see that my aluminum are not balanced. I'm going to go ahead and take care of that by adding a coefficient of 2 here and move on to my oxygen. This is a very similar example to what we began with. Oxygen are not equal. I need more on the reactant side. However, there's nothing I can take times 2. That's a whole number to get to 3. So I'm going to go with the whole number method and look at what these both go into, which is 6. Therefore, this is going to be a coefficient of 3. This is going to have to change, and so what times 3 is going to get me to 6 is 2. Again, and I put the wrong number here. I put my coefficient, that's 6. There we go. So when I did that, however, this changes my aluminum. I now have 4 aluminum, and this is no longer balanced. So balancing is handy to do either on scratch paper or with a pencil, because you are going to have to change coefficients from time to time. So I go back, I change this back to 1. I know that my coefficient then needs to be a 4 in order to balance that out. I now have equal aluminum and equal oxygen, and I'm now done. Last example. So this one I threw in because this is where things get tricky, and we're going to build on this more as the week goes on. This is a type of reaction called combustion, and we'll get into it more. However, the 3 elements that can really send you on a wild goose chase is the carbon, the hydrogen, and oxygen. Like I mentioned, oxygen will always be balanced last. Always start with oxygen at the end, okay? Hydrogen should be second to last. And then if you have carbon, balance it first. If we had other elements like sodium, a lithium, a chlorine, those would be listed above. But you always do oxygen dead last, hydrogen second to last, hydrogen third, or carbon third, hydrogen second from last. So taking an inventory, I have 1 carbon on the reactant side, 1 carbon on the product side. Hydrogens, I have 4 and 2. Oxygens, I have 2. Now, oxygen on the product side, you have to be careful. We have oxygen split up between 2 places. I have a subscript 2, subscript 1, therefore I have 3. When I get to the part of balancing, my carbons are equal, so I can move on. My hydrogens are not. I need to increase my number of hydrogens on the product side. I know that I can add a coefficient of 2, and when I do that, that changes my hydrogen to 4, and those are now balanced. However, what a lot of times students do is they say, I added a coefficient 2, I have 3 here, therefore my inventory is 6. 6 is not the correct number. You have 2 oxygen from the CO2, and you now have 2 oxygen from the H2O. So in reality, your current total of oxygen is 4. So now I need to add to my product, to the reactant side to get to 4, like on the product side. I know 2 times 2 will get that to 4. I can see that my inventory is equal in all 3 elements, and I am done. I can leave those other spots blank or fill in with a 1. So this was your first walkthrough on how to balance chemical reactions. If you have questions, need help, please let me know.